Hello there. Welcome back. In our last video, we kind of talked about the idea of a saddle point. So here's kind of a great example of a saddle point. You may recognize this as our Pringle chip or our hyperbolic paraboloid. In the very center of here, we have our saddle point. Now notice this is not a maximum or a minimum value. It's kind of in between. But what I want you to notice is in one direction, the function is concave down. But in the other direction, fx is concave up. And that you can kind of see that one, either fxx or fyy, one has to be negative while the other has to be positive. And that's going to generate our saddle point. It's just a quick example of that, of a saddle point. And now we're going to take a look at how we can identify maximums and minimums using, of course, our formula that we discussed. Remember our formula for the second derivative. We'll see that in a second. But we're given this function right here. F of xy is x plus 3 squared plus y minus 1 squared. The first question they're asking is identify the extrema by recognizing its given form. Now, hopefully we kind of recognize this. This is our elliptic paraboloid. And if we think of our elliptic paraboloid, this is going to open up. If we think about our elliptic paraboloid, it looks like this. It's going to open up right here. At the very bottom, I am going to have a minimum value. And that bottom is my critical number. So I can find the location of that point because it just comes from my shifts. So I can find the location of my critical number very easily from the shape. Now this is an easy way to do relative extrema because I know what this shape exactly looks like. My critical number is going to be at the point negative 3, 1. It's just my shift. It's my vertical and horizontal shift. Negative 3, 1. My critical point, therefore, would be if I plug that point in. Negative 3, 1. And of course, we would get 0. So our critical point would be negative 3, 1, 0. Now the question is this a relative maximum or a relative minimum? Now notice, we're not using our formula yet. We'll do that one in a second just to verify this. Just to verify that our formula works. Okay? But if I want to if I want to determine this is a relative maximum or minimum, well, I already kind of know. Because I know the shape of an elliptic paraboloid opens up, there's my bottom. I'll use my egoid of math as pretending this is my elliptic paraboloid. There's my bottom. Any point not at the bottom is going to have a greater z value than that point. And that kind of goes to what we talked about earlier when we defined a relative minimum. That all the points not at our minimum are greater than that point. And that's how we can write this. So we can write this by saying any point such that f of negative 3, 1 that does not equal, or I guess I should just keep it generic, any point in xy, or any such value xy, that does not equal the value at negative 3, 1, which equals 0, is greater than the value at negative 3, 1. Therefore, our point, negative 3, 1, 0, is a relative minimum. Now that's by recognizing it. But now let's verify this. So let's see if our partial derivative formula works. Remember, our partial derivative formula was d is fxx times fyy minus the partial of xy squared. We want to verify that this will be, again, see if our test will also give us a relative minimum value. Now, we already found our critical points. We already know those, so we don't have to redefine that. So the point that we're going to be looking at is at negative 3, 1, 0. So we need our partials. Fx, which is 2 times x plus 3. I need my second partial with respect to x, fxx, which is just 2. Fy, which is 2y minus 1. And my second partial with respect to y is just 2. And now we need fxy. And that's not too hard to do. Fx is 2x plus 3. There's no y value, so that's just going to be 0 for us. So to get d here, we are just going to multiply those together. Don't have to plug in any points here. It's going to become 2 times 2 minus 0, which is 4. 4 is greater than 0. So now I can say, since d is greater than 0, and remember, we only have to worry about the xx part in our rule, right? That's our rule, right? We only have to worry about the xx part is greater than 0. If they're both greater than 0, they're saying that that's concave up, right? Concave up, and these are both in the same direction. Therefore, we can say that negative 3, 1, 0 is a relative minimum. And that's our rule. Right there. So we can see it graphically, that's a relative minimum, and we can see it using the calculus as well. So let's take a look at another example. Classify the critical points of x, y. So I have to find my critical point. Well, find my critical points here. To do that, I might get my critical numbers, fx, which is y. So we know that y would equal 0. Fy would be x. So we also know that x would be 0. So our critical point would be f of 0, 0, which is just 0. So we get 0, 0, 0. So we want to determine, is this a relative maximum or minimum? So I take my second partial. Fxx would be 0. Fyy would also be 0 because there is no value there. So now if I take a look at fxy, well, that's just going to become 1. And I can use my formula, 0 times 0 minus, remember, it's really going to be 1 squared, which is just negative 1. So take a look. Therefore, d is less than 1, which is less than 0. It's negative right here. So we can say our rule, since d is less than 0, our point 0, 0, 0 is a saddle. Remember, that's our rule. So if d is less than 0, we have a saddle point right there. All right, let's try the next one right here. Now, again, we want to find the critical point. Now, we already found the critical points here. That was our answer to one of our other questions right here. We already found the critical points for this one, so we're just going to use those. We have 0, 0, 4, 1, 1, 3. No sense reinventing the wheel right here. So we have our critical point. Let's do the first one at 0, 0, 4. And then, of course, the other one, 1, 1, 3. So we can check them. Fx, you might remember, is 3x squared minus 3y. Fy was 3y squared minus 3x. Take the derivative with respect to x again, and that's just going to become 6x. The second fyy, and that's just going to become 6y. And of course we would need fxy as well. Fxy, that's just going to be fxy becomes negative 3. So let's use the point 0, 0, 4 first. Okay? So d would equal, now be very careful, fxx. If I plug x in for 0 here, that becomes 6 times 0, which is 0, times fyy. If I plug y as 0 here, I'm going to get 0 minus fxy squared becomes negative 3 squared, and we get negative 9. That's less than 0. So we know that 0, 0, 4 is a saddle. Ready? Let's plug the point 1, 1, 3 in. See what we get. D becomes, my x is 1, fxx, remember my rule, fxx at 1, that becomes 6 times, plug 1 in for here, 6 minus, again, this negative 3 squared. I know that's going to be greater than 0. So I know d is greater than 0, and fxx is greater than 0. So they're both greater than 0. Therefore, the point 113 is a relative minimum. And there's our answer. Right there. Alright, let's take a look at one more. We can do this one in class or another time or another video, but I want to take a look at this last one down here. It says classify all the critical points. So let's go ahead and find our critical points. Fx, if I take the derivative with respect to x, this becomes negative 1 over 3 times x squared plus y squared to the 2/3. Chain rule, don't forget to multiply by 2x on top. Fy, same thing, becomes negative 1 over, this becomes 3, this becomes x squared plus y squared to the 2/3. Chain rule again, times f by 2y. So find my critical numbers, let fx equal 0, and that's not too bad. So if I just let fx equal 0, I'm only looking at the top, so I get this negative 2x equals 0, so x is 0. Fy equal to 0. Same thing, I get this negative 2y equal to 0, y is 0. So my critical point, f of 0, 0, if I plug that in, we're going to get 0 plus 0, that's being squared, right? And that just becomes 0, 0, 1. So there's my critical point. All right, now, the second derivative is really complicated on this one. I really don't feel like taking the second derivative. So what I'm going to do is I'm going to look at this part right here. I'm going to look at this part. If I look at this x squared plus y squared, this is always going to be greater than 0. Because it's always greater than 0 and I'm subtracting it, what that tells me is that the value at 0, 0, which is 1, will always be the greatest value. Now, if you had a hard time with that, let's just kind of think about that real quick. Okay? If this is, no matter what I plug in for x and y, it's going to be subtracted from 1. Because this is always a positive value right there. So I'm always subtracting. So if I'm at 1 here, my height, anything around it is going to be less than that value right there. So we can now say, since any point, and this is another way to write it, any point xy, value xy, that does not equal the value at 0, 0, which is 1, is always less than the point 0, 0, 1. Therefore, our point 0, 0, 1 is a relative maximum value. Now, another way to write this, if you want to take a look at it, another way to write it is this, and this is a really weird way to write it, since any f of x, y, I should write it this way, not equal to 0, 0, is less than the point at 0, 0, which is 1, and then therefore it's always a relative maximum. So it's another way to say it. Any point x, y not 0, 0 is going to be less than the point 0, 0, 1. Okay, another way to write it. All right, I hope you enjoyed this video. In another video, in the next video, I will take a look at number 4 if you need that extra practice. Bye.